All right, Kate smallest product of two sorted arrays. So what we're going to do is we're going to binary search. The whole algorithm is we're going to binary search for the product where the number of products between nums1 and nums2 is less than or equal to this product. And then if that number of products is greater than k, well, that means that we have too many products. So we have to decrease our binary search, the range of our binary search. So let's just say if that number of products is greater than k, then decrease range of binary search. And if that number of products is less than or equal to k, then we want to increase the range of our binary search. And the reason we do less than or equal and not just less than here is because so when we're binary searching for a product, like for example, let's say we're trying out, let's say our midpoint was equal to say 10, and let's say that k equals 4. So this midpoint just represents the product that we're trying out. We want to know how many products are less than or equal to 10 here. And we want to find the fourth smallest product. And let's just say that the number of products less than or equal to 10 happens to be 4. If the number of products that are less than or equal to 10 is 4, well, the problem with that is that let's say our four smallest products are just 1, 2, 3, 4. Let's just say that these are the four smallest products, right? Well, these are all less than or equal to 10, but 10 isn't actually our smallest product. Isn't our fourth smallest product. It's this 4 here. So what we would do to make it easy is we would just keep binary searching. So like we would set our high equal to 10 now, and then we'd calculate our new midpoint. And let's say that our midpoint was now 5. And then we would try, okay, now how many products are less than or equal to 5? Well, notice that it's still going to be 4. The number of products that are less than or equal to 5 is these 4. It's still going to be 4. So we have to just keep binary searching. We essentially have to keep binary searching for the smallest number that results in the number of products being equal to k. Okay, so let's just get into this because I feel like I should just go through it. Go with it as I should explain as I go. So what I'm gonna do is I'm gonna create partitions of the nums1 and nums2, and I'm going to partition them to their negative elements and their positive elements. So, okay, so I'm just going to create a long array, call it neg1 for all the negative numbers in nums1, equals arrays dot stream. So all I'm doing is I'm going to take all the negative numbers out of nums1 and put them into this array here. So we're going to pass in nums1, and we're just going to say as long stream. So I'm just converting this because it gave us an integer array. I'm just converting it to a long array. And this is because I don't want to deal with like integer overflow later when we're like multiplying products and stuff. So as long stream, and then we want to filter out all the negative numbers. So we're going to say x is less than 0 and to array. Okay, cool. And then we're going to do the same thing for we're going to do 3 more because we have to do the positives, the negatives, and the positives for like nums2 as well. So let's do the positives. So pass in nums1 again, and then we just have to change this to greater or equal to 0. So now this has all of our positive numbers, and now we want to do neg2 and pos2. Okay, and we want to pass in nums2 for this, and then change this to greater or equal to 0. Cool. So now I have all my negative numbers, all my positive numbers for nums1, and all my negative numbers and my positive numbers for nums2. And now what I want to know is, okay, I want to know if k, does it fall into the range of negative products, or is it in the range of the positive products? So what I'm going to do is multiply. So first of all, how do we get the number of negative products? So int num negative products equals the neg1 dot length times pos1 or sorry, the pos2 dot length, because we have to multiply something. So we have to multiply something from nums1 by something in nums2. So what I'm going to do is I'm going to find the length of all the negative numbers in nums1 and multiply it by the positive numbers in nums2. And that is the number of negative products. But we also need to do the opposite, where we do neg2.length, so all the negative numbers in nums2 times all the positive numbers in nums1. Okay, cool. So now this is the total number of negative products. And now if, let's just create a Boolean, so let's just say is positive. And this represents whether k falls into, if the k that we're looking for, the kth product, if it falls into the range of positive products or negative products. So it's positive if k is greater than the number of negative products. Okay, so what do we want to do next? So if it's positive, so if k is in the positive range of products, then we're actually going to subtract the number of negative products from k. So now k, because we subtracted the number of negative products, so let's say k is 40 and the number of negative products is 35. Well, our new k is going to be 5, which just means that we're looking for the 5th smallest product in the range of our positive products. Okay, so yeah, we're just looking for so if k was 40 and the number of negative products is 35, then we're just looking for the 5th smallest product in our positive products. Okay, so let's just take that out. And now, because of let's go through like how we actually want to count how many products are less than or equal to some product. So for example, let's just make up some numbers. Let's just do positives for now. Let's do 1, 2, 3, 4. And we'll do our other, so let's just say this is one array, right? And we want to do the other array. So we're going to do 0, 1, 2, let's just go with 3. And let's just say I want to know how many products are less than or equal to, let's just actually type that out. How many products are less than or equal to, say, let's go with 3. So I think that's okay. So what we're going to do here is we're going to have 2 pointers. We're going to have a pointer at the beginning of the first array, and we're going to have a pointer at the end of the other array. Let's call this j. And I'm going to multiply this number by this number. So 1 times 3 is 3. And 3 is less than or equal to 3, right? Well, note, because these are sorted, I don't have to bother multiplying 1 times 2 or 1 times 1, because these numbers, if 1 times 3 is less than or equal to 3, well, that means that 1 times these decreasing numbers are also going to be less than or equal to 3. So 1 times 3 is going to be less than or equal to 3, 1 times 2 is going to be less than or equal to 3, and so on. Okay, so the number of products here is going to be whatever j is plus 1. So because j is our index, so if j is our index, then we just add 1 to get the actual number of products, right? So j is 3 here, so 3 plus 1 would be 4. Okay, so we have 4 products so far that are less than or equal to 3. And then once we're done with, now we calculated this number, let's do the next number. Now 2 times 3 is 6. 6 is not less than or equal to 3, so we have to try smaller products. How do we try smaller products? We decrement j. Because again, this is decreasing, right? So if we just keep trying smaller numbers, we'll try smaller products. So 2 times 2, that's 4. That's not less than or equal to 3. So we're going to decrement j again. 2 times 1 is 2. So 2 is less than or equal to 3. And I don't have to check this number because this is definitely going to be less than, if 2 times this number was less than or equal to 3, well, 2 times this smaller number will also be less than or equal to 3. So we just do the plus j plus 1 again. And this is going to, so this was index 1. And now 4 plus 2 is 6. Cool. And now we try the next number. And 3 times 1 is 3. And 3 is less than or equal to 3. And we just add j plus 1 again. Sorry, we add j plus 1 again to our count. So we're going to j plus 1, which is just going to be 2. It's going to be, so our total count is 8. And if you're wondering, like, why didn't I have to reset j all the way back here, right? I went straight from the 2. So this is where we were before. And I incremented the I to the 3. And now you're wondering, like, why didn't I have to go backwards? Well, let's think about it. If when I was here, 2 plus 2 times 2 was 4. And 4 is not less than or equal to 3, right? Well, if this number times this number was bigger than this number here, then remember that these are sorted. So if I just keep increasing these numbers, then if I move I here, well, these numbers are still going to be, these numbers times this product, this number here. So like if we did 3 times 2, well, those are also going to be bigger than 3. So I don't have to, so like basically what I'm saying is that if this number here didn't work out with 2, then that means that none of these numbers are going to be able to work out with this number either, because because I'm just going to keep growing. My product's just going to keep increasing as I go in this direction. So once I decrement j, I don't need to go backwards. So sorry if that's a little rough, but it's a little tough to explain. But basically, yeah, I don't have to. These numbers are just going to keep increasing my product, so I don't have to. If this number didn't work out with this, well then neither are these. Okay, so I decrement j. And we're gonna set 3 over here. And I forgot if well, whatever. 3 is less than 3. I think I added that to my count. I'm gonna assume I did. I'm gonna assume that I added the 2 numbers here to my count. I don't remember if I did or not. But anyway, so let's just say I did. Then I'm gonna increment my I, and to my next. Now that I'm to calculate the next number, and now it's 4 times 1. So that's 4. Is 4 less than or equal to 3? It's not. So we decrement j again. Is 4 times 0 less than or equal to 3? It is, because 4 times 0 is 0, and 0 is less than or equal to 3. So we just add 1 here. Cool. So now we have 9 products that are less than or equal to 3. Well, this works with positive products, this little algorithm of like counting the number of products that were less than or equal to some number. But how do we do this with like negative numbers? So like let's say that this was -1, -2, -3, and -4. And these would actually be in reverse order, right? Because this isn't in sorted order right now. This is, if it was in sorted order, this would be -4, -3, -2, -1. Okay, so now this is like sorted, right, in ascending order. So how would we run our algorithm? The exact same thing, because it doesn't work if we try it. Like let's try the same thing. So if we do -4 times 3, that's -12, and so let's just actually write that down on the side. -4 times 3 equals -12. Well, -12, even though it's less than or equal to 3, that doesn't mean that the rest of these numbers will be less than or equal to 3. Because let's just say that our the product that we were trying was, I don't know, what's a good one? -10. So if I wanted to know how many products were less than or equal to -10, well, -4 times 3 is 12. -12 is less than or equal to -10. So we could go ahead and count all these numbers. Or according to my algorithm, I should be able to count all these numbers. But that's not the case. Because remember before, if this was less than or equal to our product that we were trying, then all of these times this number must also be less than or equal to it. But that's not true. Because if we keep so if I were to like try, let's actually just look at this right here. -4 times 2 is -8. And guess what? -8. Let me put some another line. Oh shoot. Let me get rid of this. This over here. Okay, put this back. Okay. So -4 times 2 is -8. And -8 is not less than or equal to 10. Or sorry, it's not less than or equal to -10. -8 is greater than -10. So this doesn't work where we just like want to count the numbers before, but what we can do, and you just have to play around with this, like you kind of have to brainstorm and like be a little clever. Like, I tried flipping the signs, I tried reversing the orders. I was like, how can we get this to have the exact same behavior that we had for the positive numbers so that we don't have to like account for like expert cases and stuff. What I realized was I can actually reverse the positive numbers. And there was no intuition behind it. I just played around with it enough to like to realize that it worked. So I was like, well, let's just try reversing the positive numbers, right? So let's say I don't know what's a good one that we could do. Let's go with 5. So let's say that the product that we want to try is 5. So how many products are less than or equal to 5? Well, let's try our algorithm again. And now that I reverse the positive numbers, well, -4 times 0 is 0. Okay, and guess what? 0. All right, let's just do this over here. So this is going to be less than or equal to 5. Okay, cool. Now the question is, are all of these numbers times this number going to be less than or equal to 5? And the answer is yes, because these are increasing. And -4, that means that these are because I'm multiplying these increasing numbers by a negative number. That means my negative number is going to keep getting bigger and bigger. And if my negative number, so let's say this is going to be -4, right? So -4 times 1 is -4. And then the next -4 times -4 times 2 is -8. And then -4 times 3 is -12. And notice these numbers just keep getting smaller and smaller because -4 and -8, these are just decreasing. So these are all less than or equal to 5. So once I check, is this number times this number less than or equal to my midpoint, then multiplying this number by the rest of these numbers is also going to be less than or equal to this midpoint. Okay, so that's how we're going to account for the negatives. And yeah, so, and then for the positive, let's just say, I guess we have to talk about one more thing. Actually really quick. So if K is in our negative products, then I'm just going to reverse the positive arrays so that we can calculate it this way. And if K is in the positive products, well, the only other way to get positive numbers is when we multiply let's say we had -3, -2, -1. So let's say this was nums1 or let's say this is our two negative partitions, right? When we multiply these two negative partitions, so if this was neg1, I'll say this was so let's say this was neg1 and this was neg2. Then when I multiply these numbers by these numbers, I'm gonna get positive numbers. So we multiply the positives by the positives or the negatives by the negatives, and that'll give us positive numbers. Well, in order to get the same behavior as the positive numbers, when I'm like doing the whole like ij thing, so like I would have I at the beginning and j over here. What we're gonna do is we're actually going to reverse these, because if you think about the positive when we were messing with the positive numbers, we had 1, 2, 3, 4. That would be, and then we could say our other array was 1, 2, 3. Well, notice these are increasing, right? Well, when I multiply negatives by negatives, these are essentially acting as positive numbers. So, but notice that like 4, 3, 2, 1, that's decreasing. So, and like if we were to pretend like these signs weren't here, this would be decreasing. So what we want to do is we actually want to reverse the negative numbers. So we want to say -1, or we just want to reverse this, and we want to reverse this in order to have the same behavior when we were messing around with the positive numbers to count the number of products. Okay, so let's get into it. Okay, so if it's positive, we want to reverse the neg1. We want to reverse neg2. Okay, and I'm gonna write this helper function in a second. It'll be fast. And then else, if it's in the negatives, we want to reverse our positive arrays. So we're gonna reverse pos1 and reverse pos2. So remember, is positive just represents whether k is. Let me just comment. So k is in the range of positive products, else k is in the negative products. Cool. And let's write this reverse function really fast. Let's just put it down here. So we'll do, maybe put some spacing. Okay. So we'll do private void reverse, and we're just going to take in some number array. And actually, this needs to be a long because we change these to longs, right? Okay. And yeah, I think that's it. So now we just do for in I equals 0, I is less than, we'll do an ij thing. So we'll do I is less than j, plus I, decrement j, and we don't, I just forgot to declare j. So j will be set to the nums dot length minus 1. And now we want to do nums, so we want to do a swap, right? So we got to do a temp equals nums at I, and then nums at I equals nums at j, and then nums j equals temp. And if I'm struggling to type, it's because one of my keys has popped out and I have to like type with a broken key. Okay, so now we have our reverse, and I think we're good. So now we can actually move on to the binary search part of this. So now we're gonna, so what we want to do is we want to binary search for the product. I think I wrote the algorithm up here, right? So we want to binary search for the product where the number of products between nums1 and nums2 is less than or equal to that product. And then if that number of products is greater than k, we decrease the range of our binary search. And if that number of products is less than or equal to k, we increase the range of the binary search. So let me just type it out, and I think you'll see what I'm trying to get at. You'll see what that means a little more clearly if I just code it out a little bit. So let's set our low to, so I'm just going to hard code the constraints into here. So what's like our maximum negative product? Our maximum negative product, so it's going to be negative 10 to the 5th times 10 to the 5th. So that would get us, so our maximum negative product is, or basically our smallest possible product is going to be negative 10 to the 10th, right? Like if we were to multiply negative 10 to the 5th times 10 to the 5th, this would be the smallest possible product we can have based on the constraints. So the way that we're going to represent this is just do negative 1e to the 10. And I think, and I'm going to set this to a long. Okay, and then we're going to cast that to a long. Cool. And then we'll do this, and for the high, long high, we'll cast it to a long too, and then we'll just do 1e to the 10 plus 1 to be for high to be exclusive. Okay. And you could write this inclusive if you wanted to, like you could get rid of that 1. You just have to account for it in your binary search, but I'm just used to writing my binary searches with my high being exclusive. Okay, so while low is less than high, and we want to calculate a midpoint. So this is like our candidate product that we're going to try. And we're going to do low plus high minus low divided by 2. Cool. And by the way, really quick, so this low, if we wanted to be super optimal about this, like we could just find the minimum product in our nums1 and our nums2 array. So like we don't, even though I'm hard coding this, like if let's say our nums1 was like negative 3, 1, and then 2, and then our nums2 was say 4, 8, and 9. So if these were our two arrays, what we could do is we would set low to say negative 3 times negative 4. We could set it to like negative 12. And then we would set our high to 2 times 9, which would be, that would be 2 times 9, which would be 18. And then we would binary search for the correct product with it. And then, yeah, so we would just binary search between that range of negative 12 to 18. So we just do our min product and our max product. But this requires a lot of like little checks. Like you could definitely extract it out from like, because we have our negative numbers. We have our negs, we have our negative 1, our positive 1, we have our negative numbers and our positive numbers, right? From between nums1 and nums2. But it requires some checks and stuff, some like if statements, because it's like, I feel like finding, without getting too into it, like finding these negative numbers and positive numbers, that could be like its own little helper method if you were to like extract it out from this, because like these negative numbers could be empty. These positive numbers could be empty. So you got to like account for some like little, like they're easy corner cases, but they require some logic. But anyway, just wanted to throw that out there. And then you could even get more optimal. I don't even know if I should mention it, but like, because we know whether k is in the range of the positive products or if it's in the range of the negative products, we could set our high to like, if say it was in the negatives, well then we would just set our high to the maximum negative product, or if that makes sense. Like if this was our lowest negative product, and this is we would set to the maximum negative product or whatever. And then same thing for the positives, right? So we would set it our low to the lowest positive product and our high to the highest positive product in our arrays. And that would be really optimal. But anyway, continuing. Right, I'm just doing this because I'm lazy. And this is already a lot of code. So yeah. And mid plus I. 2. So this is our potential product. And now we want to count the number. So we want to do, all right, this should be a long. Okay, so let's do long count equals, so this is the number of products that are less than or equal to this midpoint. So let's just do get count. And I'm going to write this helper in a second, but so what we're going to do is if it's positive, oh man, my freaking key just keeps popping out. So if it's positive, then we want to pass in, well, we definitely want to pass in the positives, right? So pos 1 and pos 2. So all I'm saying here is give me the number of products between these two positive arrays that are less than or equal to our midpoint. Okay. And we want to add that to the number of positive products that we get from neg1 and neg2 as well, because if we multiply the numbers in neg1 by the numbers in neg2, we also get positive products. And then we're going to pass in our target, which is our midpoint. Okay, so that's if it's positive. So for our negative, we're going to pass in neg1 and pos 2, and then mid. Because if we multiply our negative number and from nums1 by the positive numbers in nums2, we'll get some negative numbers, right? And then we add that to the opposite. So the negative numbers in nums2 to the positive numbers in nums1. And pass in our midpoint. Cool. Okay, so now we have the number of products that are less than or equal to this midpoint. So now we're going to check if the number of products that we have is, if it's greater or equal to k, then we return too many products, because we only want k products. Or even if we had k products, we still have to keep trying smaller numbers, and I went over that earlier of like why. But so if our count is greater or equal to k, we either have just enough products or too many. So we're going to set our high to the midpoint, and so that we can decrease the range of our binary search. Otherwise, we don't have enough. If count will be less than k, which means we don't have enough products. So that means we need to set low equal to mid plus 1, because we want to increase the range of our binary search. Okay, cool. And now at the very end, what will end up happening is, so notice that even if count, if it equals k, let's say it equals k, right? We're going to set high equal to this midpoint here. And this just represents like the potential product that we're trying. Well, if we're setting high to mid, eventually we're going to break out, because low is going to be equal to high. That's the only way that we get out of this loop. So what we can do is just return high. And we could return low too. It doesn't matter, because low is going to be equal to high. But I'm just going to return high because I think that's a little bit more clear. Because it's, even if it equals k, I'm going to set high equal to that midpoint. And this target thing, this potential product that we're trying, that is the, eventually mid will equal the product that we're looking for. Okay. I think we just got to write get count. All right. So private, and let's change this to a long. Get count, and want to pass in, just call this nums1 and nums2, and we want to do pass in the target or the product that we're looking for. So this is just like the potential product that we're trying out. So now if, how do we want to do this? So we need to do the whole like ij thing. So we'll do int I equals 0, I less than nums 1, dot length plus plus I. And for, we'll just declare j out here. So we'll set this equal to nums2 dot length. And we can actually, so we don't even have to, I'll leave it like this because it goes with the example, but we could, no, let's just be clean about it. So we could say num1 for every number in nums1. So think of this as like my index I, where I'm going through every number. So this is, so again, this is like my index. This is the value at index I. And what I'm going to do is say while j is greater or equal to 0. Because remember, j starts at the end and we're decrementing all the way down to 0. Okay. And, okay, cool. So now we're going to say if num1 times the number at j, if it's less than or equal to our product, then that means that all the numbers to the left of j can be added to our count, or including j itself, right? So let's keep a running sum. So our count is going to be set to 0 in the beginning, and we're going to do count plus equals, and I went over this before, but it would just be j plus 1. So the current index plus 1. Okay, and we don't have to, now we're not going to keep going through, and then we can just break out at this point, because we don't need to keep trying more numbers to the left. Now, if this number, let's say the product is, if we multiply this number by this number in nums2 and it's greater than the product, well, then we need to try smaller products. So, and I went over this earlier, but we would decrement j. So now I can actually clean this up a little bit. Let's remove these brackets. And we can return our count here. So I think that's it. Let me see. Do I need anything else? Let's just run it. I think we're good. All right, what did I do wrong? Count is positive. Long cannot be converted to, why do I have an in array somewhere? Oh, these need to be longs. Oh, change all these to longs. Just change everything. Actually, this needs to be a long too. Shoot, I changed everything. Okay, sorry, I put ints everywhere. Just like a bad habit. Cannot find symbol. Num1, nums2. Wow, I put a 2 there instead of j. I'm so dumb. Error, cannot find symbol. What now? Nums2. Okay, cool. Okay, long day. What is wrong now? Nums2 long to int. Okay, well, let's just change this to an int. Okay, cool. Now what? Nums at I. Where's that even on? 72. Int temp equals, oh, it needs to be a long. Okay, cool. Index out of bounds. Where am I out of bounds? Where did I go wrong? So go through every number in nums1, and j is greater or equal to, this needs to be length minus 1. Okay, we start at the last element. All right, I'm a little tired. All right, I'm in the loopy phase. Okay, so let's use the example test cases, run it. Holy cow, it's working. Okay, let's submit it. All right, we're done. So, and there's so many ways we can like micro optimize this a little bit. Like again, I explained this, how we could optimize this. We don't even need to create these arrays here. Like we could have we didn't really do anything special, right? Like we could have just, like when I partition this, I could have just figured out the indexes. Like if I had -4, -3, and -2, 0, 1, 2, 3, 4. Like if I wanted to figure out where all my negative numbers were and all my positive numbers, well, what I could have done, I just want to mention this because there's so many little ways that we could optimize. We could have just binary searched like nums1 for the number 0. and we would have found this index here, and then we would know that everything to the left is our negatives and everything from this index forward is our positives. And if 0 wasn't in here, well then, at least in Java's binary search, so I think it's arrays.binary search, it'll actually give us the insertion point. So this would actually give us this index here. In like a weird negative sort of way, and we'd have to extract out the insertion point. But the point is, it's definitely possible to like binary search for where our positive numbers start and where our negative numbers start. And then we would have to pass around like these boundaries of like, start 1 and end 1, and then you'd have to do the same thing for nums2, right? Of like where the positives and negatives start. I mean, these are terrible variable names, but I think you guys get what I'm saying here. And then we could just pass around those like boundaries into like get count, and then you'd have to like pass in the boundaries to reverse, and what is it? I know there was something else. Oh, and then like reverse. Yeah. So we could just reverse like the parts that we want in the original nums1 and nums2, like assuming that we were allowed to modify the input. And I think what else was there? I'm pretty sure there was like one more thing. Oh, we could like break out sooner in here. Like as soon as we have too many products, like if we passed in we could also pass in, so get count. If we would have passed in k into get count, then as soon as we have too many products, so like if count is, or let's just do it here. If count was greater than k, then we could just return count, because it doesn't actually matter if we could like it doesn't matter if we could like keep incrementing count past like k. We just need to return we just need to know if we are over k or not. But anyway, so there's like so many little things that you could do to like micro optimize all over the place. I think that's the major ones, though. I don't think there's any other big ones. But anyway, the time complexity is going to be O of, let's go over it. So it's going to be O of n. No, wait, what am I doing? So here, our get count method is going to be O of, let's just actually go over this one first. So this is going to be O of n1 plus n2. So this is the number of elements in nums1, number of elements in nums2. And that's because, and I know this looks like it should be like n1 times n2. It's not, because we never reset j. J just keeps moving along. Like if you guys remember how I went over it earlier, but basically because j never gets like reset, eventually we're going to, we'll go through all of the elements in nums1, and then we'll go through all the elements in j in the worst case, or all the elements in nums2 in the worst case, which just ends up being n1 plus n2. But the big idea is that we just never reset j to anything. Like we don't do like, but okay, I think that's a good enough explanation. So that's going to be n1 plus n2, and then let's see what else. Obviously this is going to be O of n space, but we could have done it in O of 1 if we really wanted to pass around like that, like indexes that represent the boundaries. And then let's see what else. Oh, the binary search. So this is going to be like big O of the log of, what is this, 10 billion, whatever. This would be 1 e to the 10th times 2, right? And normally I know that constants are like technically this is a constant, right? But I think this constant is so big, it's definitely worth noting. Like, I don't think you'd want to say that this is O of 1. So in this case, I think it's okay. I would definitely argue that this constant is big enough to warrant saying that this is a log of a constant or whatever. But anyway, yeah, definitely. I was okay. I'll just stop there. But we could have changed this to O of log of the like min product and the max product, or what would it be? It would be like, because I showed earlier how we could have just like grabbed the maximum product and the minimum product, so you could do like the max minus min, something like that. I'm a little tired, but it would be something like this. And then yeah, I think we're good. So this whole thing would just be O of 2 times 1e10 times the log, or sorry, times, or this should be log of 2, because this was our binary search, times n plus m. So let's put that in parentheses. Okay, cool. So that's our time, and then the space was just O of n plus m. Or that would be the space, O of n plus m, because we stored the negatives and positives. Okay. All right, that's it for this video. Sorry if it was a little slow or if it was a little rough. But yeah, I did my best. All right, bye.